So one of the reasons why atmospheric dynamics is so complicated and interesting is because of a phenomenon called the Coriolis Effect. And in short, the Coriolis Effect makes things that travel a long distance in the air on Earth appear as if they were moving at a curve rather than a straight line. And this effect was first described in 1833 by Gaspard Gustave de Coriolis. And at this time we had no beard, short hair, and scarf. So I'll try and explain the Coriolis effect from the perspective of two observers. If you have one person standing at the pole up here, here's the pole, and let's say they're 6 feet away from the pole, so they're just standing there. So in one day they'll go around a circle, and the radius of this circle is 6 feet. So they will travel at a speed of 0.00005 miles per hour. Now, as a side note, why is that the case? Well, they travel 2 pi r by the time that it takes, so that's your velocity, which is 2 pi times 6 feet, which is about 2 meters, divided by 24 hours. And if you perform that calculation and make sure that you turn 2 meters into miles, you'll get 5 times 10 to the minus 5 miles per hour, approximately. Okay, so now a second person standing at the equator. So this person travels in one day much further and much faster than the person near the pole. Here we have about 25,000 miles that you travel in one day, and that gives this guy a speed of roughly 1,040 miles per hour. Now imagine the following situation. Imagine that player 1 here has a soccer ball and wants to shoot it down toward player 2. And he shoots it in a straight line. Let me redraw this actually as a straight line. Okay, so player 1 is up here with his ball, and he shoots exactly at the moment when player 2 is exactly south of him, down here. So in this point, for an external observer, what we see is if player 1 shoots, he'll shoot the ball in a straight line south. But since player number 2 here travels so much faster, by the time the ball has reached the equator, player 2 will have traveled a significant distance to the east here. So if you put yourself in the shoes of player 1 here, who's looking down towards the equator, the straight line is always this line connecting him and player 2, whereas the ball ends up being deflected to the west here. That's what it looks like for the player number 1. And so if player number 2 was shooting a ball upward, trying to shoot it northward, player number 1 would be left behind. So this is, let's call them number 1 and number 2. And the ball would be deflected to the right. So deflection in the northern hemisphere is always clockwise to the right. And if you were doing the same in the southern hemisphere, shoot it towards the pole in that way, it's always counterclockwise to the left. And that's what we call the Coriolis effect. And it applies to things that travel in the air, like currents in the air or airplanes. And what's important to remember is the Coriolis force, which appears to be deflecting an object from its straight line trajectory, is not actually a force. The Coriolis effect is simply due to the relative velocity between the traveling ball and the ground on the Earth changing as you go from equator to pole.